Welcome everyone. It is my pleasure to be here. My name is Hyunong Choi and I am a professor at Department of Industrial and Management Systems Engineering from Gyeonggi University in South Korea. And today I will be delivering a lecture on the topic Technologies for Energy Transition, Building a Stable and Smart Green Grid. And before we start, let me introduce myself and my work briefly. As I mentioned earlier, I am a professor at the Gyeonggi University and the director of the Technology and Data Intelligence Lab. My research focuses on how technology can solve complex challenges in our society with focus on energy and IT technologies. To give you a better idea of my work, here are three keywords I focus on. The first keyword is social acceptance. I investigate how the public perceives and accepts newly introduced energy infrastructure or policies, which is a critical factor for successful implementation. The second is economic and environmental analysis. I conduct economic feasibility and environmental impact analysis for new technologies using various data-driven approaches. The third is emerging technologies. I apply machine learning and pattern analysis to identify emerging sustainable technologies that are likely to disrupt and shape our future. Now, back to the lecture. Today's topic is Technologies for Energy Transition, Building a Stable and Smart Green Grid. We will explore the technical backbone required to make a sustainable energy system a reality. So our journey today is divided into 4 chapters to help us understand the full scope of grid modernization and realization of the smart grid. First, we will understand the principle, the fundamental physics of the grid. Second, we will look at the challenges posed by renewables. Third, we will explore our toolbox as for key tools for modernizing infrastructure. Finally, we will discuss integration and how we orchestrate various components into an intelligent, unified system. So now, let's begin with our first chapter, the principle. Before we discuss advanced solutions, we must first understand the basic rules of the game, the physics that keeps a power grid running smoothly. So think of a power grid as a giant scale. Supply and demand must always match to maintain a stable frequency. In Korea, we maintain a standard frequency of 60 Hz, allowing for a tiny margin of only 0.2 Hz. If the scale tips, if demand exceeds supply or vice versa, the frequency fluctuates, and if not corrected immediately, the entire power system can collapse, leading to a blackout. So in the past, this balance was maintained by the power of inertia. So grid inertia is the inherent resistance of a power system to rapid changes in frequency derived from the stored kinetic energy of rotating synchronous generators. So traditional coal and nuclear plants use massive rotating turbines, as shown in picture in this slide. This heavy rotation acts as a flywheel, providing natural resistance to rapid frequency changes. It serves as a crucial shock absorber for the grid, helping the grid maintain stability. Next, we will discuss about the current, mainly AC versus DC. So the 20th century was the era of AC, the alternating current. And this was primarily because it was easy to transform voltage and cost efficient for centralized generation and one-way transmission. However, there are problems with AC. First, it is hard to synchronize between grids. In order to synchronize multiple AC grids, voltage, frequency, and pace must be perfectly aligned. If not, it causes severe grid instability or immediate blackouts. On the other hand, DC grids can flexibly connect asynchronous grids. Moreover, AC is hard to control flow. The AC electricity naturally flows along the path of least resistance. It is difficult to send electricity specifically from point A to point C if point B offers lower resistance. On the other hand, DC grids can precisely control the direction and amount of power flow. So due to problems I just mentioned with AC, today we are moving toward the era of DC. Solar panels, batteries, and EVs naturally operate on direct current. And digital devices and data centers also run on DC. Therefore, by using DC grids, we can reduce energy losses from AC-DC conversion and improve overall system efficiency. Now, next, moving on to our second chapter, the challenge. We will now see how the rise of renewable energy is shaking the traditional grid. So the traditional grid was stable as both supply and demand were predictable. However, the future grid may be unstable as supply becomes unpredictable or less predictable due to renewables and demand becomes more dynamic. In other words, we are shifting from a stable scale to a constantly tilting scale. So as I mentioned earlier, renewables are shaking the grid. This can be explained into three topics: variability and intermittency, supply-demand mismatch, and curtailment. One thing to note is that variability and intermittency is the inherent characteristics of the new renewables, and supply-demand mismatch and curtailment are corresponding results of these characteristics in the grid. First, we will look into the variability and intermittency. For renewables like solar and wind, fuel is free but unpredictable. The generation depends entirely on weather, and variability and intermittency explain such changes in power generation due to weather. Variability is about generation varying by time, and intermittency is about generation sometimes dropping to zero. Due to this variability and intermittency problem, the scale vibrates constantly over time, making it hard to keep the frequencies stable. Therefore, we need a way to cope with these problems by storing or transmitting abundant energy or shifting demand. Next is this supply-demand mismatch. The supply-demand mismatch can occur in terms of time and location. In terms of time, it can happen due to variability and intermittency of renewables I just explained. In terms of location, it can happen due to different deployment of power supply and demand between regions. Obviously, not all regions are viable for solar and wind power generation. And due to supply-demand mismatch, the scale also vibrates between regions, making it hard to match frequency between different locations. Therefore, we need a way to efficiently synchronize multiple locations or construct an independent grid that can be self-sufficient. Finally, the curtailment. Curtailment is some kind of paradox. We have too much clean energy, so we have to throw it away. Due to variability and intermittency, abundant energy must be curtailed to avoid system failure under certain circumstances. So have you ever seen wind turbines standing still on a windy day as pictured on the right? This may be because curtailment for grid stability. Due to curtailment, the overall efficiency of renewable power generation decreases. In other words, the actual contribution of renewables may be lower than expected due to curtailment problem. Therefore, we need a way to store or shift this energy. So to solve the previously mentioned problems, we need a toolbox, which is the first part of our solution. So in this section, we focus on three key tools for grid modernization: ESS to store energy, HVDC to connect grids, and AMI to collect data. These tools can be explained as key hardware technologies that can be used for grid modernization and realizing smart grid. Now, let's look at the first tool in our toolbox, the Energy Storage System or ESS. I like to call this as a time machine. Its primary function is time shifting. By charging at noon, when supply exceeds demand, and discharging at evening when demand is higher, ESS provides a clear solution to the variability problem of renewable energy. Moreover, it can also perform frequency regulation, which means injecting power in milliseconds to stabilize the grid frequency, effectively replacing the inertia lost from traditional power plants. So let's look at a specific case of ESS in Korea. So the KEPCO has built one of the world's largest ESS complexes dedicated to frequency regulation. Over 376 megawatts of ESS has been installed nationwide uh, in locations such as Anseong and Yongin solely for these four purposes. This allows us to replace coal plants that were previously kept running just for standby for grid stability, usually known as the spinning reserve. So by introducing FRESS, this project saves approximately 13 million US dollar per year in fuel cost and significantly reduces carbon emissions. Next, our second tool is HVDC or high voltage direct current. I call this the superhighway. So HVDC has a major advantage over AC. It suffers far less energy loss over long distances. Moreover, it also allows for the precise control of power flow direction and amount, which is essential for stabilizing the grid scale. We can use HVDC strategically to connect remote renewable energy zones to major demand centers, solving the regional mismatch between supply and demand. The Jeju HVDC project illustrates the most representative case about this technology. So as you can see from the picture, the lines number 1 and 2, which were completed in late 90s, were supply driven, sending power from the mainland to Jeju Island to solve shortages. However, the line number 3, which was completed in 2024, is stability driven. As our first bi-directional line, it can now send Jeju's surplus wind power back to the mainland, solving the problem of curtailment and stabilizing the entire grid. For your information, Jeju is the largest island in Korea and has a windy weather, which makes it an optimal place for wind power generation. The final tool in the toolbox is AMI, the data collector. This is a two-way digital meter that sends electricity usage data every 15 minutes. Without AMI, it is impossible to implement modern mechanisms like demand response, DR, or time of use, TOU, pricing. Korea has rolled out AMI to over 22.5 million households, creating a big data platform that enables new energy services and improves security. Moving on to the final part of our lecture, the solution to integration. So the hardware tools I introduce alone are insufficient by its own. The real key to a modern grid is how we orchestrate these components into a system. We focus on four types of integration: physical integration through microgrids, virtual integration through VPPs, mechanism integration through demand response, and sector integration through P2X. These integrations are key to grid modernization and realizing smart grid. The first is the microgrid. A microgrid is a self-sufficient energy system capable of islanding or disconnecting from the main utility grid. Its key components are ESS and renewables. This system is best for local systems such as islands, remote villages, or industrial campuses where reliance on traditional large central grids can be expensive. A representative example for this microgrid is Gapado, a small island south of Jeju. By combining wind turbines, rooftop solar, ESS, and heat pumps, Gapado achieved 100% energy self-sufficiency for days. It serves as an ideal mini testbed for grid independence via microgrid. So while it has some issues in the past, additional government projects are expected in the future in this region and other candidate sites. And the second is the VPP, or virtual power plant. This system aggregates thousands of small resources like solar, ESS, and EVs using information and communication technology. It is called a virtual power plant as it operates like a single large power plant without actually building a physical power plant. The Jeju VPP pilot project is the most representative case, which allowed small renewable owners to bid in the electricity market, enhancing overall grid reliability. Next, the third is demand response, or DR, which is our market-based integration. Since the value of energy changes depending on time of the day with higher renewable energy penetration, governments use DR to shift demand with price signals. So Jeju's plus DR is the key example. When renewable generation is too high, the system essentially says, we will pay you to consume electricity. This intensifies EV charging or factory operations during midday surpluses to stabilize the grid without shutting down wind turbines in Jeju Island. Finally, we have P2X, or sector coupling. This breaks down the walls between the power grid and other sectors like transport, heat, and gas. The logic is simple. Electricity is hard or expensive to store, whereas molecules like gas or heat are relatively easier and cheaper to store. First, the P2M, or power to mobility, treats EVs as batteries on wheels. Through the vehicle-to-grid V2G technology and bidirectional chargers, EVs can discharge power back to the grid during peak hours. This allows EVs to act as a distributed ESS network, which can also earn profit for the EV owners. Jeju is also doing V2G pilot project on collaboration with Hyundai Motor Group, which is the largest automotive maker in the country. Next, P2G, power to gas, involves using surplus renewable energy to produce green hydrogen. By using extra renewable energy for water electrolysis, we can create green hydrogen, which enables long-duration seasonal storage. In Jeju, a P2G pilot project converts wind energy into hydrogen fuel to power city buses in Hamdok region. Next, P2H, or power to heat, uses surplus electricity to run large heat pumps or electric boilers. This heat can be used for district heating, industrial complexes, or agricultural facilities. Storing heat is significantly cheaper than storing electricity using batteries, making this a highly efficient solution. Jeju is also planning P2H pilot project, which aims to provide heating service for tourist attractions and agricultural facilities. Finally, I would like to introduce P2X combined with CCUS, carbon capture, utilization, and storage. So CCUS technologies are technologies that capture carbon dioxide from the atmosphere, power plants, and industrial facilities, and either utilize it productively or store it permanently underground. So by combining green hydrogen with captured industrial CO2, we can produce environmental friendly e-fuels like e-methanol. So e-fuels are synthetic fuels produced by combining green hydrogen generated through water electrolysis using renewable electricity with captured carbon dioxide, CO2, from air or industrial sources. So in Korea, projects in Ulsan industrial complexes are capturing industrial carbon to create clean marine fuels, which have solved grid saturation while reducing overall emissions. So finally, to recap our learning journey, I would like to mention key takeaways of the lecture. We began by exploring the physics of the grid, where we learned that maintaining frequency through inertia is like keeping a giant scale in balance. We then identified the challenges posed by renewables, specifically the issues of the variability and the painful necessity of curtailment. To solve these, we opened our toolbox, like looking at the power highways of HVDC and digital shock absorbers of ESS and AMI. Finally, we discussed the orchestration of the entire system through integrated solutions like microgrids, VPPs, and P2X. So to conclude, you might ask, why look for Korea about this technology? So there are several reasons. And the first, the Korea has established a clear blueprint with long-term policies like carbon neutrality 2050 to realize these technologies. Moreover, we possess world-class technological capabilities in ESS, HVDC, and AMI. Finally, we have extensive experience managing and testing these future energy systems in sites like Jeju and Ulsan. So, building a smart green grid is not just about laying wires. It's about connecting components and creating value. And we look forward to sharing these experiences and technologies as you build your own sustainable futures. And thank you for your attention.